Hello everyone, welcome to our discussion of section 8.1 where we will begin to talk about polar coordinates. Now there are several things that are important about polar coordinates. First of all is that the notation that you see on the screen here, that refers no longer to the x and y coordinates but to a distance from the pole or origin, we call r, and theta, which is the angle between the positive x-axis and the terminal side of the angle. And number two, we talk about an interpretation of polar coordinates when r, when that distance is negative. And also, we talk about equivalent polar coordinates. Now, when we were talking about regular trigonometric functions and angles, there were some, as you know, all the trigonometric functions are periodic in nature, so they can add up to different, the same angle can add up to different angles, such as pi plus 2 pi plus, depending on what kind of a trigonometric function we have. If you have tangent function, then the same angle plus pi will give you the same location, or if you have sine or cosine function, the same angle plus 2 pi will give you the same angle. So those would be equivalent angles depending on the period of the trigonometric function. With polar coordinates, we have the same situation where one angle can be represented in different equivalent forms. We will look at that. And of course, number 4, which is extremely important, is that there is a relationship between what we know as x and y coordinates, or the rectangular coordinate system, and the polar coordinate system. There is a relationship, and we will look at those formulas as well. So let's begin by just covering the basic aspects of polar coordinates. So if we draw two small figures here, and let's get our y-axis here and here. Suppose then we have some point, let's say 1 here, and 1 point, let's say here. Up to now, we know that the coordinates for these points would be x, some x value and some y value, right? But in the polar coordinate system, then, we have, instead of x and y, we have r comma theta here, and we have r comma theta here. So what do these the r and theta represent? Well, if we connect a line from the origin, by the way, let me also label this. So in the polar coordinate system, this point, which we knew up to now the origin, it's called pole, or the origin we know of up to this point. And also here, let me refer to that as pole or the origin. If that's pole, then what is the polar axis? That is the question. So the polar axis is the x-axis. So, so let's write that down also, that x-axis is equivalent to the polar axis. So the origin is the pole in the polar coordinate system, and the x-axis is the polar axis. Having said that, then, if we connect a line from the pole to the point with x and y coordinate system, then this length here, this distance from the pole to that point, it's called the R. That's what you see there, R. And let's do the same thing here as well. That. And we have R here. All right. And then theta represents the angle from the positive side of the x-axis. So we're not anywhere along the x-axis, but from the positive side of the x-axis to the terminal side of the angle that we're looking for. So this would be here. This would be that. That represents theta. And in this figure, this distance or this angle represents the theta in that polar coordinate system. So theta in the polar coordinate system is the angle from the positive side of the x-axis to the terminal side of that angle that we have. Together, they give us the perfect location for that point. And let me write this down as well as we define the polar axis. So theta is the angle between the positive x-axis and the terminal side of that angle. Okay, so these are how we describe the polar coordinates of a point. All right, next, let's just give some basic examples of finding the coordinate, the polar coordinates of a point. So we'll look at just a few simple examples. So suppose, for example, we want to find a point with polar coordinates 4, 2 pi over 3. Okay, so the first thing we would do, that is, we in the coordinate coordinate system. Okay, we want to locate that in the regular coordinate system that we have with first quadrant, second quadrant, third quadrant, and fourth quadrant. We want to locate that point. So let's call this x, and then, right, that's the coordinate system we're used to. Now 4 is the distance from the pole to that point, but that, let's look at that next, but the first thing is figuring out this angle. So if this is 2 pi over 3, would it be in the first quadrant or the second quadrant? Well, it would be in the second quadrant, because if you had 3 pi over 3, that would reduce to a pi, right? Just pi. 3 pi over 3 would be just pi, but we have 2 pi over 3, which is a little bit smaller than pi. So it would have to be, this point would have to be in the second quadrant. So we are here, okay? And let's actually put a point here. To be exact, we would say that 2 pi over 3, so pi minus pi over 3 is equal to 2 pi over 3, right? When you take the common denominator, we get 2 pi over 3. Okay, so the difference is we are pi over 3 or 60 degrees short of, from this point, to get to the negative side of the x-axis. So this is this would be the terminal side of the angle from the positive side of the x-axis. So if we are here, then where the theta would be that angle from the positive side of the x-axis to the terminal side. This is theta equals 2 pi over 3, and then this distance would have to be 4 units from the pole. It could be any units. So let's just say r is equal to 4, and it's that distance from the pole to the point. Okay. All right, so we want to, let's give another example. We want to find, this time, find or locate, maybe it would be a better word, find or locate the point 1, let's say, comma 0, in the rectangular coordinate system. Which would be the same xy coordinate system. Okay, so I forgot to mention, please pause the video as you look at each example and write down your own solution on a scratch paper before seeing my solution, and that way your brain basically processes information in a more deep and permanent way rather than copying this stuff down. Copying the material down, it will not help you learn this material long term, but if you write down your solution first and then look at my solution, your brain will store that information in a more permanent way because it's connected to what your thinking is. And so please don't forget to do that, to pause the video and write down your own solution first. So here, 1 represents the distance from the pole to some point, 1 unit. It could be 1 kilometer, it could be 1 meter or 1 inch. And 0 represents the angle from the positive side of the x-axis. It's 0. So we are on the x-axis. So let's, I will just use one of my thick markers here to draw that. So we are here on the x-axis because the angle from the terminal side to the positive side of the x-axis is 0. So we're on the x-axis. And let's put a point right there. And I should have maybe also labeled this point, this one before, in the previous example, as 4, comma 2 pi over 3. So that's that point. And here, we want to label this. So this distance, this is r equals 1. And that point, 1, comma 0, that's that point. All right, and that's that. So this is, again, this would be r, and that is theta. Okay. All right. Maybe that was too easy, huh? So let's look at another more interesting example. Suppose we want to find or locate the point, let's say 6 and negative 7 pi over 6 in the rectangular coordinate system. Okay, so I'm counting on you that you're pausing, and on a piece of scratch paper you're drawing your own graph before you look at what I have. Okay, so let's do that here. X and y-axis here, like that. So notice that this is negative angle, and one of the first lessons we learned in this course is that if you have a negative angle, that goes in the clockwise direction. So counterclockwise is positive direction, negative is clockwise direction. Now if we had, so where would this angle be, right? Which quadrant would it be if we're going in the clockwise direction? Well, if this was negative 6 pi over 6, and it's a little bit larger than that, right? It's 7 pi over 6. If it was negative 6 pi over 6, this would be negative pi, right? The 6 and 6 would cancel out. We would get minus pi, which would mean go from here clockwise pi degrees. So we would go this way. But this is a little bit larger than that. So we can't stop here. We would go into the second quadrant, moving in the clockwise direction from the positive side of the x-axis. So this would be somewhere here. And let's draw a line from the pole or the origin to that point, like that. So that angle, negative 7 pi over 6, would be this angle from the positive side of the x-axis to that. Like this. And that distance is, of course, 6 units. Okay, and that would be 6 comma negative 7 pi over 6. Right, so it would be just to find that. So this difference from the negative side of the x-axis to the terminal side, or otherwise known as the reference angle, is just pi over 6. So to get to that, we would, in other words, let me write it down. So theta being negative 7 pi over 6 is the same thing as going negative pi and then additionally another negative pi over 6. And that would be negative 7 pi over 6. Okay, so that distance here is, reference angle is pi over 6, that difference here. Okay, like that. All right, so this is just a few examples in exploring how to locate a point using its polar coordinates. So now, when r is negative, when this r is negative, so far, take a notice that everything we did, r was positive, right? 4, and then 1, and then 6 here. These were all positive r values. When r is negative, then there is a different interpretation of the location of the polar coordinates. So we will look at that. This is pretty important. So important note. If r, which is one of the coordinates of the polar, in the polar system, if r is negative, then r theta or r comma theta. So it is a distance absolute value of r in the direction opposite to theta. So in opposite to theta. Okay, so let's look at a couple examples as to what this means. So we want to, in this example, we want to show, let's say show the difference actually, show the difference between P1, let's say P1 equaling 2 comma pi over 3, and the same point with the exception that this r is negative. So and P2, let's call this equaling negative 2 comma pi over 3. Okay, so let's see what the difference is just by drawing these 2 points. And that would be, so this is the description of what we mean, but let's draw it so you have a picture in mind about what that description means. So if we draw, let's say, so we have our x-axis here and the y-axis. So let's start with this P1, right? We know how to plot that. Pi over 3 is for sure in the first quadrant. So that would be 60 degrees from the positive side of the x-axis. Let's say somewhere here. So this is where P1 is with the coordinates 2 comma pi over 3. And 2 would be, let's say, 2 units distance from the pole to that point, like that. Okay. So this would be r equals 2, right? Now, for this P2, all this description is saying is that when r is negative, then what you would get with the r being positive, which is that, now it would be on the opposite side, or pi, in a pi angle from that point. That would make it opposite to this theta, right? So if this is theta, let's say, let's call it, this is theta, right? Equals, in this case, pi over 3. So with this negative in front of r, or negative r value, the other point, let me draw that with this thicker marker that I have. It would be pi or 180 degrees on the other side. That's what it means when we say in the direction opposite to theta. So it would be, the difference would be pi away from that. So that would be that. Okay, so that would be here. And this would be, let me, actually I just noticed my drawing is in a way that might indicate that this is the coordinates of that. No, this point is connected to this point, this coordinate. Okay, so that's that. And then this one, we have P2 equaling minus 2 comma pi over 3. So this is important, right? Because even though this location is theta plus pi from the positive x-axis, notice that the theta is still saying pi over 3. So you should be able to distinguish between this point and that point, because this angle, even though it says pi over 3, it's theta pi over 3 plus pi away from the positive side of the x-axis. So why is that? Is because of this negative r value. So to find this point, you would find that point, and then noticing that this would be opposite to that, you would simply mirror the location of that point in this quadrant, in this third quadrant. Right? So that's why this is important, because you shouldn't plot this point in the first quadrant. Why? Because the r value is negative. So you would maybe start by saying, oh, okay, if this is positive, it would be in the first quadrant, but it's not. It should be in the opposite direction, in the opposite quadrant, so to speak. So it would be in this location. Okay, so that's pretty important thing to remember with respect to the polar coordinates. So let's do another example. Suppose we want to show the location of this point. The location of this one, so negative 5. Right away you notice that the r is negative, right? Negative 5 comma negative 17 pi over 6. So that's a large angle. But notice that it's negative, so we're moving in the clockwise direction from the x-axis. So if we draw this, and again, I'm assuming that you're pausing the video and drawing these on a piece of scratch paper before you see my solution. And if you do that, I'll be very grateful to you, because I know you'll learn this subject very well if you do that. And so that. Okay. So first of all, notice that how do we figure out where this theta is? It's such a large angle, and we shouldn't need a calculator for this. We can easily imagine this. If this was minus 18 pi over 6, that would simplify to minus 3 pi, right? If this was minus 18 pi over 6. So minus 3 pi would mean going around, starting from the positive x-axis and going clockwise. If we go one full revolution, that would be minus 2 pi, but that would be minus 3 pi. So we would come to this point, but this is not minus 18 pi over 6. This is minus 17 pi over 6. So it's a little bit, or pi over 6 shorter than the angle that would be minus 18 pi over 6. So we would end up in the third quadrant. But the path to get to that point would look like something like this. So first we would go minus 2 pi, right? Let's do it that way. So we would go around. So that's 2 pi, minus 2 pi, right? Going in the clockwise direction. From here to here, that's minus 2 pi. For minus 3 pi, we would have to go another minus pi to this side, but we have minus 7, so it's a minus pi over 6, or pi over 6 shorter before we get to this side of the x-axis. So we can continue it continue the path for this angle, let's say that to this point, and then stop there and say that, okay, our angle would be that, right? So I'm going to draw these dashed because none of this, it's that angle yet. We haven't found that angle yet. So let me, and I don't have my pencil with me, so I'd rather use a pencil at this point, right? So if this 5, which is r, was positive, this is where we would end up, that point. Because that trace, the red marks, the dashed red line, would be then minus 17 pi over 6. And positive 5 would put this point 5 units from the pole. But it's minus 5. So that's not the location we are. We are 180 degrees or on the opposite side. So our point would be on this side, directly opposite to that. So let's draw that here. And I'm going to use my thick marker just to make sure that I highlight the difference between the actual location and what this would have been if it was 5 comma negative 17 pi over 6. So this is that angle. Okay, so that point is where we are, where that angle is. So this is minus 5 comma minus 17 pi over 6. Again, you see how important this is to know how to handle negative r values, because this angle is, if you didn't know this, this is certainly not the angle from the terminal side of this angle and the positive x-axis, right? This is just pi over 6. But that angle is negative 17 pi over 6. However, this is the actual location because it's directly opposite to where it would have been if we had r equal positive 5. Okay, so that's where the actual location of this point is. All right, so that's that. Then we have equivalent forms of a polar coordinates. Like I said, this is we did this earlier with the regular locations of angles, such as for sine and cosine. If you have pi over 3, you can write the same angle for sine and cosine by saying pi over 3 plus 2 pi, right? You will be back at the same spot. Those pi over 3 for sine and cosine functions, pi over 3 and pi over 3 plus 2 pi are the same angles. In the polar coordinate system, we have the same configuration. Let's see how that works. So these are let's call it finding equivalent polar coordinates. Okay, so we want to do that. So this is how we find equivalent polar coordinates, and we have so let's call it equivalent location for some point r comma theta are these. So we have P as r comma theta plus 2n pi, right? Theta plus n being 0, 1, 2, or any integer basically, and we will write that down. And let me actually write that down here. N is any integer like that. And then another equivalent form could be obtained using the negative r value. So negative r, comma, this time theta plus 2n pi. So what would this negative, after our discussion about when r is negative, what happens to the location? Notice that when r is negative, the point is thrown off to the opposite side pi degrees, right? Or 180 degrees when that is negative. So we need, in order to correct that, when r is negative, we need to add another pi in order to bring it back to its original location. So this would be plus pi. Okay, I keep referring back to these last two examples that we did. Notice how with negative r value, the location of that point was thrown off pi, right? We went 180 degrees. There was a difference, 180 degrees difference between this, which has the same theta, notice, but different r values. One is negative, the other one is positive. And same thing happened here, right? So this point, so that point would have been, this point would have been 5 comma 17 pi over 6, right? But of course we have negative 5 comma that. So again, that point is, the location of that point is changed over a pi angle. It's the opposite side. So to correct that, because we're looking for equivalent locations of the same point, because of r being negative, that location is off by 180 degrees. So in order to bring it back to that same location, we have to add pi to it. So let me actually highlight, because this negative is the reason we're adding pi. Okay? Do you notice the difference? So without this negative, notice we don't have plus pi. It would be just r comma theta plus 2n pi. It would be the same thing. But if I put minus in front, then we add pi. Okay, just to bring the point back to the correct or equivalent location as this point. All right, so this is, I probably want to box this. So let's do some examples for this. Suppose we want to find the equivalent forms. Equivalent forms, that means both forms, where r is positive and we have a negative r. So in both forms. Equivalent forms for this point, which has this polar coordinate, like that, 7 comma pi over 4. Maybe I can bring, this is better, so you can see that and this on the screen. Okay, so the equivalent form, so first let's call it first equivalent form, right? So like that. So we take the same r, and then that angle, or pi over 4, we can pick n to be any integer. Let's pick the easiest one, n equals 1, right? You could pick n being 2 or 3. So you could pick any number, any integer, but I'm just picking the easiest one. So one equivalent form would be 7, a point that has r equals 7, and then pi over 4 plus 2 pi, and I'll just write when n equals 1. Okay? So that's one form. I'm going to leave it like that. But if you want, you can take the common denominator and write down 9 pi over 4. It's the same thing. Okay? And then the second equivalent form, we would make use of this. So we will make this r negative and then add another pi to this, making this 3 pi, right? So second equivalent form would be minus 7 comma pi over 4 plus 2 pi. Again, I'm using n equals 1. If you prefer, you can use n equals 10. And then that would be another equivalent form. 2 pi plus pi, which would mean p, and then, or point p, negatives with coordinates r negative 7 comma pi over 4 plus 3 pi. Okay, so these two are the equivalent forms for the same angle. Okay. Let's do another example. So once again, we want to find the equivalent it goes without saying that here, when we say equivalent forms, we mean equivalent polar forms. And I should make that clear here as well. Equivalent polar forms. For this point, 2 comma 3 pi over 4. Okay, that point. All right, so we're going to use the same thing, same formulas here. So the first equivalent form, and again, there are many, many correct answers, so I'm just picking one where n equals 1. We can have same point, so we have 2, we keep this positive 2, and then 3 pi over 4 plus 2 pi. So that's one form. So this p for just for point. And then the second equivalent form if we make this r value negative, right? So negative 2 comma 3 pi over 4 plus 2 pi, which we did there, and then add another pi to it in order to bring the point back to that location. So it would be plus pi again, and then let me add those two. So we have negative 2 comma 3 pi over 4 plus 3 pi. Okay, like that. So these are equivalent polar forms. All right, so that's that. So we come to the very important topic of the relationship between the coordinate system that we are familiar with, or the rectangular coordinate system xy, and the polar coordinate system. Okay, so I will actually, let's talk about it this way. So let me just say changing from, because we can change coordinates from rectangular system to polar and from polar to rectangular system. So let's start by saying changing changing polar to rectangular coordinates. I think it's changing polar to rectangular coordinates. Okay, and then we'll do the opposite, from rectangular to polar coordinates. Okay, so let's draw a graph here. If we have a graph like this, x and then y, and let's say we have some point here with coordinates r comma theta. Okay. Also, that same point has coordinates that are x comma y, right? That we are familiar with already. And so I want to draw a line from the pole or the origin to that point. And then, so that's of course r. That is r. And this angle from the positive x-axis to the terminal side is theta. And that distance, so this is showing both coordinate systems for the same point. So this distance would be y, right? That distance, we know it to be y. And then also from here to here was x, right? From here to here, and then from here to here would be y. So now, if we write down, so how can we connect these two coordinate systems? That's an interesting subject. So let's do that. So if we have, for this point, then sine of theta would give us the y, right? We already know that. Y, so let's write it down here. So sine of theta would be equal to y, or the opposite side to this angle, divided by the hypotenuse of that triangle. Okay? So this then translates into a nice equation that gives us y coordinates in terms of the polar coordinates. So r times sine of theta. R sine of theta. Okay, that's one. We can do the same thing for x by considering the cosine of theta, right? Because cosine of theta is the adjacent side, or x, divided by the hypotenuse of that supposed right triangle. So let's do that. Cosine of theta is equal to the adjacent, or x, divided by the hypotenuse, or r. And that gives us a nice equation for x. So x equals the r, right? Just cross multiply, r cosine of theta. So with these two equations, then we can easily, given the polar coordinates r and theta, we can find y and x, right? You can take r, multiply it by sine of theta, and you get y, and r times cosine of theta, you get x. Okay, so that's to do that. So let's then also do the reverse, which is changing when we have rectangular coordinates and we want to change them back to polar coordinates. So changing rectangular to polar coordinates. And I want to separate these two, so that. We have formulas for this too. So for this, we have r squared this time. So this is what we have to remember. R squared, I want to use my blue ink here. R squared would be equal to x squared plus y squared, right? And that should be obvious from this picture because it's just a right triangle, and we're finding, using the Pythagorean theorem, to locate the r value, which would be r squared equals x squared plus y squared, right? Just using the Pythagorean theorem. But for our case, we're making use of that to find r. If you know r squared, you know r, because you simply take the square root of that value, and you get r. And also for tangent of theta, or theta, the angle theta, well, I want to break this into two parts. So looking at this figure, tangent of theta would be the opposite divided by the adjacent, right? We need that. We need to use tangent because we're going from rectangular to polar coordinates. And if you know the rectangular coordinates, that means you have y and x already. So tangent of theta helps you find that, and then we'll have to take the inverse of that, of course. So let me just write it as this. Tangent of theta is equal to y over x. And then, of course, x shouldn't be 0. But then the theta, let me actually use a different color here for this, because this formula is the intermediary before we find theta, which is the part of the polar coordinate. So this isn't going to give us theta, as you know. This is just tangent of theta, but it makes use of the rectangular coordinate system. Once we have that, then we can say theta is equal to inverse tangent of that quantity. So inverse tangent of y over x. And let me just say x not equal to 0. Okay. And we want to also box this. These are these formulas, and these are very important. Okay, we will be working with these a lot. So just remember, the tangent is just the intermediary. This is the one that you really want to use then to find theta. This will give you r indirectly, because once you know r squared using the Pythagorean theorem, then you can take the square root and find r, and then theta is obtained using that, inverse of that tangent. Okay, so let's do some examples then. So suppose we want to find the rectangular coordinates whose polar coordinates are -1 comma 5 pi over 2. Okay, so we want to go from polar to rectangular coordinates. So please pause the video at this point, or you want to maybe rewind or look in your book and write down these formulas, because you're going to need to know these formulas going from polar to rectangular. You're going to need these. And then pause the video and write down your own solution before you look at what I have. Okay? All right, so I'm assuming you've done that, and now you're back. So using these formulas then, let me bring them back. So x would be r times cosine of theta, right? Our theta is 5 pi over 2, and our r is -1. And that would give us x. So let's start with that. So x is equal to r cosine of theta. So this would be, let's plug in. Oops, sorry about that. So -1 times cosine of 5 pi over 2. Now you know that any pi over 2 and any multiples of pi over 2 are, of cosine of any such angle would be 0, right? So this is equals -1 times 0, or x equals 0 basically. So x equals 0. Okay, so we have that. Then for y, we have r sine theta, right? So let's make use of that. So r being -1 times sine of 5 pi over 2. And this piece is, of course, 1 times -1. We get -1, right? So y is equal to -1. Okay, so with these two then, the rectangular coordinates are 0, -1. So let's call it x, 1 is equal to 0, -1. Okay, this is our answer for that one. Let's do another example. These are easy examples, but that's good because we always want to start easy and build up from that. So let's do another one here. Here we want to convert rectangular coordinates. Let me make sure that I'm on the screen there. So minus square root of 6, comma, minus square root of 2. Okay. Which quadrant is that? Right? Which quadrant is that? So x is negative, y is negative. There is only one quadrant where both coordinates are negative, and that's in the third quadrant, right? So convert that to polar coordinates with r greater than 0 and theta. So they want us to, because r, as you know, can be positive or negative, and they want us to keep it positive. So theta being between 0 and 2 pi. Okay. All right. So please take a few minutes, maybe 10-15 minutes, and write down your own solution and then come back to the video. All right, so here we're going the opposite of what we, are we doing that? No, we're actually going convert the rectangular coordinates for the point to polar coordinates. So yes, so we're going the opposite. Yes, that's correct. So here we were looking for the rectangular coordinates given the polar coordinate. Here we want to convert the rectangular coordinates given that we have the polar one. Okay, so here our formulas will be these, right? For r, we're going to need to use this formula, r squared equals x squared plus y squared. That's easy because this is our x, this is the y. So r squared is equal to this squared plus that squared, and then we can take the square root of that to find value of r, right? So that's easy. And then theta would be also pretty straightforward using this formula. We will first use this intermediary formula. So this would be tangent of theta equaling y divided by x, and then take the inverse tangent of that to find theta. Okay? So let's do that. R squared. So using r squared equals x squared plus y squared, then we have r squared is, so x squared is that, minus square root of 6 squared plus y squared, which is minus square root of 2 squared. Okay, so this is 6 plus positive 2, we get 8, right? We get 8 here. So r squared equals 8, which means r is equal to square root of 8. And they told us, as you know, using this square root property, if you take the square root of both sides, you will get plus or minus square root of 8, which is plus or minus 2 square root of 2. But they said to polar coordinates with r equals positive, right? So we toss out the negative piece and we keep the positive one. Therefore, r is equal to square root of 8, which means r is equal to 2 square root of 2. Right? So that's r. So 8 is 4 times 2, and 4 is 2 squared, so it can leave the square root. That's what we have. This 2 was 4 on the inside. It came out. It's now 2 times square root of 2, which is what we have left under the radical expression. Now, the angle is, finding the angle is much more interesting. Here's why. So tangent of theta, well, let me bring this up so it's on the screen. So tangent of theta would be the y value divided by x, right? So negative square root of 2 divided by negative square root of 6. So what we would end up with is positive square root of 2 over a square root of 6. Now, you can find this. You can calculate this. You can take the inverse of this, and it will give you some decimal in radians for theta. But let's see if we can find the exact value, because I want to take you through this path, finding the exact value of theta rather than a decimal form, because I think your homework wants you to do that. In the homework, you'll have to enter an exact answer, such as pi over 3 or 5 pi over 2, something like that. They won't accept if you enter decimal values. So let's see how we can derive the theta from this in exact form, not in decimal form. For that, So let me actually write that down, so when you read the notes, it makes sense to you why we're doing this and why we're not using the calculator. So finding theta in exact form. Okay? So we know that basically if tangent of theta equals that, then let's separate this to something that would be familiar to us. So we have tangent of theta equals 1 over square root of 3 times, right? I'm breaking this part up. I'm breaking this part. Let me, to make sure that everybody can follow this. So we break this up into 1 over square root of 3 times square root of 2 over square root of 2. Square root of 2 over square root of 2 is just 1, right? This is just 1. So we're multiplying that by 1 over square root of 3. Now, the reason I did this, it's because 1 over square root of 3 is the same thing if you rational as square root of 3 over 3. Let me bring my scratch paper here. So 1 over square root of 3, after you rationalize it, which means multiply it by square root of 3 over square root of 3, rationalize the denominator, what do you get? You get square root of 3 over 3, right? Now, if that wasn't familiar to you, that for sure is, because we've been dealing with the tangent of an angle that is equal to square root of 3 over 3 in the past several times on many occasions, right? So that angle is pi over 6. The reason I say that, because tangent of pi over 6, just recalling from the table of common trigonometric values of angles, tangent of pi over 6 is equal to sine. Let me first work this out on my scratch paper here. So tangent of pi over 6 is equal to sine of pi over 6 divided by cosine of pi over 6, right? And from the table of common trigonometric angle values, we have sine of pi over 6 is equal to 1 over 2, and cosine of pi over 6 is equal to square root of 3 over 2. Then, when you cancel the 2's, what do you end up with? You end up with 1 over square root of 3, right? Which is this familiar, and that's why I'm breaking up what the angle we had into that. And then after you rationalize this, you got square root of 3 over 3. After we did this, we got this for tangent of pi over 6. We got, or 30 degrees, we got square root of 3 over 3. Right? So, so that's why I broke this up into this, because we want to give the exact answer, which will help you figure out things when you complete the online homework. So now that we have that, we know this piece, this is just 1, and so 1 times that, we have tangent, we found the reference angle for the actual angle we're looking for. So this would be, from this, then this is, how do I want to write this? So this would be equal to, so the inverse tangent of this angle, it would be inverse tangent of, that's just 1, so leave it out. So just find the inverse tangent of that. That is equal to inverse tangent of square root of 3 over 3, right, after rationalizing. Which means, so I should, however, here put in, let me use my thicker marker here to put theta equals that, because I made the transition from tangent of theta to inverse tangent, so I should make it clear that this is theta that we have. From this, we can write that for theta. And that, therefore, theta is equal to, in this situation, pi over 6, but this is from this. But remember, we have both. In the beginning, I asked you in which quadrant we are, right? So pi over, if I just write down pi over 6, so let me write that down and then I'll explain. Pi over 6 from this operation, let me add quickly, not theta yet, theta for our polar coordinate. Not yet, because this is in the first quadrant. So you don't want, this is just, so now you know that the angle that you have has a reference angle equal to pi over 6 with the x-axis. But as I mentioned earlier, because both of these coordinates in the rectangular coordinate system are negative, so we're in the third quadrant. So in the third quadrant, and I think I can draw a picture here, so a little picture would help. When you're here in the third quadrant, everything we've done so far, it's very useful because we've figured the reference angle is pi over 6, but we are in the third quadrant because of these two guys, negative, negative, right? So we're here. We're here, and that angle is pi over 6. That's what we found, the reference angle, from this terminal side to this negative side of the x-axis. The real angle for our polar coordinate should be that. That's the theta we're looking for, okay, because we are in the third quadrant. And what would that angle be? We can easily find it because we know what reference angle we have, right? So simply take pi and add pi over 6 to it, and you get the theta that we need. So let's do that. So we have, so theta then, let me write it in blue. So theta for our coordinate system is pi over 6 plus pi, or 7 pi over 6. We did all of this gymnastics over this because we want to give the theta in exact form, not in decimal form. Again, this is helpful for when you complete the online homework. So this is the theta. This is the actual theta we need, that one. And you have r. We figured out r here, and the theta here. Therefore, the coordinates are, the polar coordinates are 2 square root of 2 comma 7 pi over 6. Like that. Okay, that's the polar coordinate. If I can, so this is the polar coordinate for this rectangular coordinate. Of course, if the online homework didn't specify that you give the exact answer, this would be much easier. We could just give some approximate decimal value for the theta in radians. Okay, so that's that. So let's do some more examples along the same lines of converting from polar to rectangular coordinates and from rectangular to polar coordinates. So this would be additional example in that along the same line. So we want to here convert the equation x squared plus y squared equals 9. Of course, what form is this? This is rectangular coordinate system, right? Rectangular equation. 2, so we want to go from here to polar form. Okay. This is a little bit different than the previous 2 examples that we did. So again, please pause the video. Spend about 15 minutes at most, but use your own mind to solve this. Then come back to the video, and I'm counting on that you're doing that. Okay, so remember that when we go from rectangular to polar form, we have these formulas, right? So we have, well, here's the formulas that we have. Let me write it down. So x in the rectangular coordinate system is equivalent to r cosine of theta, and y is equivalent to r sine of theta, right? So why don't we then plug for x with its equivalent in polar form, for y with its equivalent in polar form. Let's do that. So substituting, we have r cosine of theta squared plus for y squared we have r sine of theta, too many parentheses, so I'll just write sine theta squared equals 9. Well, what do we have here? Then let's distribute the power. What do we get? We get r squared cosine squared theta plus r squared sine squared theta equals 9, right? What can we do with it? Can we simplify this? What do you think? We can, right? Let's factor out r squared. We get cosine squared theta plus sine squared theta equals 9. I'm sure you remember by now, we've used this squared identity, trigonometric identity a lot before. This is equal to, what is this equal to? That's equal to 1, right? So recall that cosine squared theta plus sine squared theta equals 1. Right? So let's substitute. R squared times 1 is equal to 9. So r squared times 1 equals 9, which means r squared equals 9. Like this. Okay? I hope this agrees with the solution you had when you worked this out on the scratch paper. So here is another example. We want to convert y equals x squared. This is again in what form? In rectangular form, right? X and y we have. To polar form. Okay, once again, we have so I'm counting on the fact that you may have paused the video and already gotten your own solution. That would be great. So once again, x equals r cosine of theta, and y equals r sine of theta, right? These are the formulas we have. Let's plug in. For y, we're going to plug in with this. So we have, thus, we have on this side, we have r sine theta equals, on that side, we have r cosine theta squared, like that. So then if we distribute the power, what do we get? We get r, on the left we still have r sine theta. Then distribute this, what do we get? R squared times cosine squared theta, right? So we're almost there, right? We almost have our polar equation. So let's move this r sine theta to this side. It will make this negative and set the whole thing equal to 0. So r squared cosine squared theta minus, move this to the other side, r sine theta equals, if we move this, then we have nothing left on that side. So this is, so we began with our equation in rectangular form, and we were able to convert it to polar form. Okay, so this is what we have. Equation in polar form. So not only we can convert coordinates from one form to the other, we can convert whole equations from one form to the next. So that's what we're doing. We're converting equations from one form to the next. Okay, so let's do more examples. Suppose we want to convert r equals 7. What form is that? It's polar form, right? This equation is in polar form. Convert this equation in polar form to rectangular form. Okay, so again, please pause the video. Make sure that you have your own solution ready before you have a look at what I have. Really, I think I mentioned this before, my solutions are worthless by themselves. They have value only if you have your own solution written down, because they help you modify your own thinking. So an important piece is your own solutions. It doesn't matter if your solutions may have mistakes in them. They're valuable because they come from your mind, and you're not just copying down my solutions. Okay, so we already know that r squared, so we know that, so r squared, because we're going from this polar form to rectangular form, we need to know what r squared, we need to remember this formula. R squared is equal to x squared plus y squared. Remember that? Now this is r, so that's no problem though. We can square both sides, right? Squaring both sides, we get r squared equals 49. So squaring both sides, if you don't do that, it's fine. I mean, if you take the square root, but normally we don't want to, if we can help it, we don't want to deal with square roots of expressions like this. So that's why I say, rather than take the square root, plug this in and take the square root of both sides and end up with an expression like that, just go the opposite way. Just square both sides. You get an equivalent forms. Squaring both sides of r equals 7, we have this, r squared equals 49, right? This is much better, because now you can say, oh, I have the equivalent form of r squared in the rectangular system is that. So you can just plug it in and get x squared plus y squared, which is r squared, equals 49. Right? You can do that. So we can either, I mean, let me do it both ways. So either that, or you can take the square root of both sides and say that square root of x squared plus y squared equals, take the square root of that, and you get 7. Okay, so we're taking r as positive in this case. So either that or that should be fine. Okay, and this is rectangular form, this is rectangular form of that. It looks different, but it looks different than that, but it's the same thing. Okay, so let's do another example. We want to convert this polar equation, r equals -3, to rectangular form. Okay, so once again, we remember that r squared is equal to x squared plus y squared, right? So let's say recall that r squared equals x squared plus y squared. This is coming from earlier when we introduced these formulas, and this is based on the Pythagorean theorem. So let's plug in. So we plug that in, and once again, let's square both sides. Squaring both sides of r equals -3, we have r squared equals +9, right? If we square both sides. So now, simply on the left side, plug in with its equivalent in the rectangular coordinate system. So we have x squared plus y squared equals 9. And this equation, of course, represents that circle, right, with a radius 3, centered at the origin. We're familiar with that from Math 126. Okay. Okay, so let's do another example. Suppose we want to convert this equation in polar form, r equals 2 cosecant of theta, to rectangular form. Okay. So please take a moment, a few minutes, 10, 15 minutes. Work this out on a piece of scratch paper on your own, and then come back to the video. Okay, so first of all, it's always easier to deal with sine and cosine rather than cosecant and secant, right? So what I would do is just recall, that's what I would do, start with, recall that cosecant of theta is equal to 1 over sine of theta, right? Cosecant is the reciprocal of the sine function, and vice versa. Sine is the reciprocal of the cosecant function. So knowing that, then let's plug that inside here. Let's do that. So we have r equals 2. I'm just substituting in here with its equivalent. 2 times 1 over sine theta. So we would do that anyway, but especially here because there's a connection between the rectangular coordinates and sine and cosine, but there is no such connection between, not direct connection between rectangular coordinates and cosecant and secant, but the direct connection is between x and y and sine and cosine. So that's another good reason for us to convert from cosecant to sine. Now that we have that, then we have let me take this step by step, 2 over sine theta
Now we can cross multiply, right? The denominator here is 1. 1. So cross multiply, what do we get? From here to here, we get r times sine theta equals 2. Does the left side look familiar? It should, right? Let me see if I bring back that when we introduce the formulas on page 5. R sine theta represents what? Represents y, right? So that's what we have. So what we have is y equals 2. Because, well, so we know that y equals r sine theta. So I'll just add that in. So therefore, y equals 2. So we have the rectangular form of that polar equation is a horizontal line going through y equals 2. Okay, so that's that. And then we have another example. So we have, let's convert this equation in polar form, r equals, so as soon as I write r, you know you have an equation in polar form. To rectangular form. Okay? So please take a few minutes, work this out on your own before you watch the rest of this solution. So the first thing we would do is just like before, because if we are to convert this to rectangular form, we have to have r times sine theta or r times cosine theta, right? So we have to cross multiply in order to get a product of r and one of these trigonometric functions. So let's cross multiply, and we get denominator here is 1, and after that we have r times 1 minus cosine of theta equals 2 times 1 is just 2, right? So 2 times 1. Let me write the steps fully. So let's distribute this. So we have r minus r cosine of theta equals 2, right? What is that piece? We know that, right? Let's see. Let me bring back those. So r cosine theta is x. So let's replace for now. We're not done yet, but r minus x equals 2. What do we have? We have r. Let's move everything to everything that is not r to the other side. We have x plus 2, right? So now, because remember that we have r squared equals x squared plus y squared, right? So r is the square root of x squared plus y squared. But again, if we can avoid having square roots in our equation, all we care about is convert this polar form to rectangular form. Now, if the rectangular form does not have square roots in it, we would prefer that. So because of that, let's square both sides. Okay, so let's not keep things like this. So squaring both sides, so note, squaring both sides. that's the whole reason behind why I say let's square both sides. That's the whole reason. So let's do that. We end up with r squared equals x plus 2 squared, right? Now, recall that r squared is equal to x squared plus y squared. Maybe if I bring that back, if I, because I want you guys to connect what you're seeing to the previous slides, right? Remember that? On page 5, we had r squared equals x squared plus y squared when we were talking about changing forms, one form to the other, right? We have that. So that is coming from that. Recall that. And now on the left, replace it with its equivalent. So on the left side, we have the following. So we substitute x squared plus y squared equals x plus 2 squared. And of course, we don't want to leave things like this because there's a lot we can simplify here. So let's simplify it. We've got our rectangular form, but it's not in simplified form. So let's expand the right side. Now let's combine things. If you move everything to one side, well, so let's do this. So if we have x squared plus y squared, I guess, plus y squared minus x squared minus 4x minus 4 equals 0. So we can then cancel out these two. We end up with y squared minus 4x minus 4 equals 0. If you want to, I probably, because we're used to having y on one side and x and the other constants on the other side. So maybe it's better to simplify it like this. Actually, it's better to do it like this. So y squared equals, move the other terms to the other side, 4x plus 4. So this would be our final form. Again, this is just to have the y on one side and x and constants to the other on the other side, since that's what we're used to. Okay, so that's that. Let's look at other examples that might be helpful in our understanding of how to convert equations from one form to the other. So let's convert this form, r equals 4 over 1 plus 2 sine theta, to rectangular form. Okay. So once again, because we're rectangular form, the connection between rectangular and polar form always has r multiplied by either sine or cosine. Let's cross multiply so we get that. So we get r times that. Okay, so, and please work this out on a piece of scratch paper, especially now that we've done so many examples. You should be able to answer this and then come back to the video after that. I'm counting on you that you're doing that. So we have r times 1 plus 2 sine theta equals 4 times 1, right? We get that. So let's distribute the r. We get r plus 2r sine theta equals 4. Of course, you know by now that this r sine theta represents what? X or y? Represents y, right? So we can write then r plus 2y equals 4. And then let's move this to the other side. So what do we get? We get r equals 4 minus 2y, right? And then just like the previous example, when I mentioned that you can substitute for r with square root of x squared plus y squared, but you end up with square root in your equation. So squaring both sides has the benefit of obtaining a rectangular form that does not contain any square root. So let's do that. Let's square both sides here. So we get, so squaring both sides, we have r squared equals 4 minus 2y squared, right? Great. So let's replace and also recall that r squared is equal to x squared plus y squared. I keep bringing this back because you guys have to remember these in order to be able to answer these questions. See, r squared equals x squared plus y squared. So I'm using that. That's what I'm recalling. That, substitute that on the left side. And then so we have recall that and substituting we have x squared plus y squared equals 4 minus 2y squared. Right? Okay, great. So now let's expand the right side and combine the like terms and simplify our equation. So we have x squared plus y squared equals 16 minus 16y plus 4y squared, right? So how do we want, let's move everything in this case to one side. So we have, I'm just going to move these two terms to that side. So 4y squared minus 16y plus 16 stay as they are. And then minus x squared minus y squared equals 0. So if we simplify this, 4y squared minus that, we get 3y squared. And then we have another squared term there. So let's bring that next. We have minus x squared, and then minus 16y, and then plus 16 should be equal to 0. Is that, so did I do that right? Minus 16y. Let's see what I have here. Just making double checking everything here. So we have, so 3y squared minus, double checking that. So that's correct. This is correct. Yeah, that's correct. So that like that. Okay, like that. All right, maybe we should do one more example. I think that would be good. So let's do that. So we'll do one more example. So suppose we want to convert r equals 16 divided by 1 plus 4 sine theta to rectangular form. Okay. Okay, I'm counting that you've already done your solution. You pause the video as soon as I wrote that down. You're done and now you're back. So once again, we need a product of the r and the sine or cosine if we had here in order to generate a rectangular form. That combination would help us to generate a rectangular form. So let's do that. So r times all of that let's distribute this. We get r plus 4r sine theta equals 16. So you already know, we've done this before, so that's equal y, right? This is equal to y. So what we have here is r plus 4y equals 16. Let's move everything that is not r to the other side. So we have r equals 16 minus 4y. Just like before, let's square both sides, right? We know the benefit of that. We're not going to end up with a square root in our equation. So squaring both sides, we have r squared equals 16 minus 4y squared. So on the right, what do we have? On the left, we have, well, we know that, so we know that r squared is equal to x squared plus y squared, right? So plug in on the left and then expand the right side. So we get x squared plus y squared equals 16 squared is 256, I believe. 256. Then 2, 8, and that's minus 128 y, and then plus 16y squared. Okay, that's the expansion of the binomial on the right. And then, so once again, let's move everything to one side and set it equal to 0. So we have, what do we have here? Okay, so I'm going to move these to that side just because there are fewer terms to move. So 16y squared, those three stay on that side, minus 128y, and plus 256. I'm thinking because if you have things like this in your online homework, your answer may be different, and I hope the online homework is set up in a way that it will accept your answer as long as it's correct. Because if you move these three terms to the other side, I was just thinking, you're going to get an answer that looks different, but it's exactly the same as what I will get. But I don't know in terms of the online homework how that will be interpreted by the software. So if you suspect that you have the correct answer in the online homework, but you're not being credited for it, please let me know. I will look at it, and if your answer is correct, then I will give you full credit for that. So let's simplify this. 16y squared minus y squared, we get 15y squared, like that. And then we have another squared term here. Let's keep that here, minus x squared. And then we have minus 128y plus 256, and that is equal to 0. And I will double check with this. So minus x squared, this is correct. Yeah, that should be correct. So this wraps up our discussion of our first discussion of the polar coordinates, and we will, in the upcoming sections, we will look more into details of this. And I thank you for watching this video until this point. And for now, have a nice day, and I hope to see you again next time.